So this is not going to be a regular video, and this is a review for integrals as net change in volume from my high school math class. But these are still good practice problems, so follow along if you want to. So the first problem is find the area of the region in the first quadrant enclosed by y equals 4 minus x squared, y equals 3x, and the y-axis. So first, go to your graphing calculator and insert the equations. 4 minus x squared, 3x, and then graph it. And what we need to find is the area bounded by these in the first quadrant with the y-axis, so it's going to be this like triangle looking area here. And what we can do is find the left bound and the right bound and calculate the definite integral of the upper curve of these bounds and then subtract that with the definite integral of the lower curve. So the upper one is going to be 4 minus x squared and the lower one is going to be 3x. And to calculate the intersect, which is our right bound, we can do this. And the left bound is obviously x equals 0. And the right bound is going to be x equals 1. So what we can do is go here and calculate the integral from 0 to 1 from the upper curve, which is 4 minus x squared, and minus that with the integral of the lower curve. And we can just put all this into one equation. And we get our answer of 2.16, which is 13 over 6. So this one will just be from 0 to 1, 4 minus x squared, 3x, which is 13 over 6. And that's our final answer. Second problem is find the area of the region between the graphs of y equals cube root of x and y equals x squared minus 2x minus 8. So first, let's put these into the graphing calculator. So x squared minus 2x minus 8 and cube root of x. And it's going to look something like this. And again, to find the area between the two curves, you just take the definite integral of the top one and subtract the definite integral of the bottom one from it. So it's going to be the definite integral from a to b of the top one. So this is cube root of x minus this x squared minus 2x minus 8. And now let's find our bounds, what are a and b, which is to intersect to calculate them. The first one is negative 1.79, and we're going to have to round it so it's not exact, but from negative 1.79 to the other intersect, this one is 4.26. So our b is going to be 4.26. And now put this into our calculator. Negative 1.79, 4.26 from cube root of x minus x squared minus 2x minus 8 with respect to x. Is that right? Yeah. And our answer is going to be, wait for it, 39.2. So 39.2 units squared. And that's our final answer. The third problem is find the volume of the solid generated by rotating the region bounded by the graphs y equals 1/2 x, x equals 6, and the x-axis about the x-axis. So let's put these into the graphing calculator. So y equals 1/2 x, or 0.5 x, and x equals 6. And the trick to doing this is putting a bunch of 9s and then your x intercept like that, and then when you graph it, it just appears as a straight line. So we need to find the solid generator rotating the region bounded by the graphs. So it's going to be this triangle, and we're rotating it about the x-axis. So what it's going to be is a definite integral from 0 to 6, because those are our bounds, of pi r squared, where r is the radius, or the y value of each little thing. So the y value is just going to be 1/2 x squared dx, and then we can put this into our graphing calculator, and it's just going to be definite integral from 0 to 6 pi times 0.5 x squared, this back to x, and our answer is 56.5. So that's our final answer. Number 4 says, find the volume of the solid generated by rotating the region bounded by the graphs of x equals 5 minus y squared and x equals y minus 1 about the line x equals -4. And we can notice that all of these equations are like x equals something in terms of y. So what we can do is swap the y's and x's, and if we do that, the area we get, or the volume we get, will still be the same. So y equals 5 minus x squared, y equals x minus 1, and y equals -4. And now let's put these on the graphing calculator. So 5 minus x squared, x minus 1, and -4. And this is what it looks like. And we want to rotate this area, the area bounded by the two curves, around y equals -4. But what we can do is move everything up 4 units. So instead of rotating around y equals -4, we rotate around the x-axis. So if we move it up 4 units, it will be 9 minus x squared. X minus 1 turns to x plus 3. -4 turns into 0. And this is what the graph looks like now. And this is just a definite integral, like a normal thing, using the Washer method. So it will be from 0, or -3, to 2, of pi times the upper curve, which is our 9 minus x squared, minus pi times our lower curve, which is x plus 3 squared dx. And we put this into our calculator. -3 to 2 pi times 9 minus x squared minus pi times x plus 3 squared dx. And our answer is 654.5. So 654.5 units cubed as our final answer. For the fifth problem, it's let R be the region bounded by the graphs of y equals 2x cubed, y equals 0, and y equals 3 minus x. So it's just this shaded region right here that they've given us on this picture. We need to find the area of the region. And for this one, we need to separate it into two separate definite integrals. One for when y equals 2x cubed is the one directly above the x-axis, and one for when y equals 3 minus x is the one directly above the x-axis. And your equations are going to be 0 to 1 for 2x cubed dx plus 1 to 3, 3 of 3 minus x dx. And putting this into the calculator, you can just do like this. 2 times x cubed dx plus definite integral from 1 to 3 of 3 minus x dx, and that is 2.5. So our final answer for part A is 2.5 units squared. Part B is find the volume of the solid generated by rotating art around the x-axis. And again, we can split this into two. First, integral would be pi times 0 to 1, 2x cubed squared. And then the second one will be 1 to 3 of 3 minus x squared, or yeah, times pi respect to x. And put this into the calculator. You can do pi times the definite integral 0 to 1 of 2 times x cubed squared dx plus pi times definite integral 1 to 3 of 3 minus x squared with respect to x. And you get 10.2. So 10.2 units cubed is our final answer for part B. Part C says find the volume of the solid generated by rotating r about the y-axis. And for this one, well, what we can do is imagine this part is shaded in two, and then find the volume of the solid generated by this, and then subtract this part. So it's going to be like two circles. You subtract one solid from another. So our bounds are going to be 0 to 2, just by looking at the graph, from pi r squared. And the first one, the large one, is going to be y equals 3 minus x, but in terms of x. So x equals 3 minus y squared. And then you subtract pi times the second one, the smaller one squared, and the smaller one, the one on the left, is 2 times x cubed. And in terms of x, that is cube root of y over 2. And then you square that, dy. Or you could substitute all of the y's for x's when plugging it into your calculator. So you just do integral from 0 to 2 of pi times 3 minus x squared minus pi times the cube root of x over 2 squared with respect to x. And our answer should be 23.5. 23.5 units cubed is our final answer for part C. Part D says the region R is the base of a solid. For this solid, cross-sections perpendicular to the y-axis are semicircles. Find the volume of this solid. So this region R is going to be the base for a solid, where it's like a semicircle, like a 3D semicircle. Basically, instead of taking the sum of all the heights, we're taking the sum of semicircles. And this is just going to be like kind of like part C, where we're taking the definite integral from the y-axis. So it's going to be from 0 to 2 of pi times the diameter squared over 8 dx, because this is the formula for a semicircle, and we need to figure out what the diameter is. Diameter is just going to be from here to here minus from here to here. That's going to be 3 minus y minus the cube root of y over 2. So we can rewrite this as 3 minus y minus the cube root of y over 2 squared over 8 dy. and plug this into our calculator. We can do definite integral 0 to 2 times or pi times 3 minus x minus cube root of x over 2 squared all over the 8 and then with respect to x. And that's going to be 1.69. So our final answer is going to be 1.69 units cubed. Number 6 is let R be the region in the first quadrant bounded by the graphs of y equals 1 over x plus 2 and x equals 4. Part A is find the volume of the solid generated by rotating R about the line y equals -1. And again, like part 4, we can move all these up by 1 unit, so this turns into y equals 0 over the x-axis, and this is y equals 1 over x plus 2 plus 1. And now the graph looks something like this, the asymptote right here instead of the x-axis, and we want to find the area rotated around. But since we have to use the Walsh method for this, we have to find at what y value is this asymptote, so we have to subtract it from the definite integral. And this is just at y equals 1 because that's how much we added to both these equations. So our definite integral is going to be from 0 to 4 of pi times 1 over x plus 2 plus 1 squared minus pi times 1 squared dx, and plug this into the calculator. So definite integral from 0 to 4 of pi times 1 over x plus 2 plus 1 squared minus pi times 1 dx. And our answer is 7.95. So 7.95 units cubed is our final answer for part A. And part B is find the volume of the solid generated by rotating R about the line y equals 3. For this one, let's move everything down 3 units, so y equals 0 and 1 over x plus 2 minus 3. And the graph will look something like this, with the asymptote right here, and this being the area. And what we can do is let's flip it over the x-axis and then do it that way, because right now it's under, so taking the definite integral would be kind of weird. So instead of this, it will be y equals 3 minus 1 over x plus 2. And now that's going to look something like this, the asymptote right here. And now what we can do is see this asymptote is our upper curve, and this 3 minus 1 over x plus 2 is our lower curve. So our definite integral from 0 to 4 is going to be pi times the upper one, which is 3 squared, minus pi times the lower curve, which is our 3 minus 1 over x plus 2 squared dx. And then we put this into our calculator. Integral from 0 to 4 pi times 3 squared plus or minus pi times 3 minus 1 over x plus 2 squared dx. And our answer is 19.7. So 19.7 units cubed is our answer for part B. C is the vertical line x equals k divides the region into two regions of equal area. Find the value of k. So let's say, first let's calculate the whole area of the entire thing. Definite integral from 0 to 4 of 1 over x plus 2 dx. Pretty easy, just put that into your calculator. 0 to 4, 1 divided by x plus 2 dx. That is 1.0986 whatever. And now divide this by 2 to find the area of what one region should be, 0.549. So now we can say from 0 to some value b of this is equal to 0.549. And we need to find this value b, or this value k actually, because that's where the vertical line should be. So now we can use the fundamental theorem of calculus. First, integrate this 1 over x plus 2. That would just be ln of x plus 2. And insert k minus ln of 0 plus 2, which is 2. It's equal to 0.549. So ln of k plus 2 is equal to 0.549 plus ln of 2. So we add ln 2 to this. That is 1.242 whatever. And this means e to the power of this is equal to k plus 2. So e to the power of our answer is equal to k plus 2. We subtract 2. We should get our answer of 1.46. So we get k equals 1.46. And that's our final answer. Part D is the region R is the base of a solid. For this solid, cross-sections perpendicular to the x-axis are equilateral triangles. Find the volume of this solid. So instead of summing heights, we're summing triangles, and it's still going to be a definite integral from 0 to 4, but instead of just 1 over x plus 2, it's going to be the formula for an equilateral triangle, with one of the sides being 1 over x plus 2. So the formula is square root of 3 over 4 times 1 over x plus 2 squared dx. Let's put this into the calculator. From 0 to 4, square root of 3 over 4 times 1 over x plus 2 squared dx. And our answer is 0.144. So 0.144 units cubed is our final answer.